Hello everybody. Today we're going to prove the fundamental theorem of algebra using Liouville's theorem, and we'll do it in about 4 short lines. So what does the theorem say? It states that every non-constant polynomial has a root, that is some z0 such that f of z0 is equal to 0. And of course we're talking about a complex polynomial with complex coefficients, which can be seen in purple. Great, so it is going to be a proof by contradiction. So 1, assume that there does not exist a root. That is, there does not exist a z0 such that f of z0 is equal to 0. Well, then it follows logically that there must be a real positive number that lower bounds the modulus of f of z, and that's because we need to prevent f of z from being 0. 2, by our assumption, since we stated that f of z is never equal to 0, we can define g of z, which is equal to 1 over f of z, and we'll state that this is holomorphic. And we can say it's holomorphic because it's the quotient of holomorphic functions, and f of z0 is not equal to 0, and f of z0 is holomorphic because it's a polynomial. 3, by Liouville's theorem, we'll say that g is unbounded. Now, how do we do this? In purple, or blue, sorry, you'll see Liouville's theorem. If f is holomorphic, if f is bounded, then f is constant. Well, we'll use the contrapositive of this, because of course g of z is not constant, as we assume that f of z is not constant, and we know that g is holomorphic, so by contrapositive, g must be unbounded. Great. Now that we made this claim, 4 states that there is a contradiction, because 3 says that g is unbounded, but if we look back to statement 1, where it says m is less than the modulus of f of z, if we take the inverse, then we'll see that g of z is actually upper bounded by 1 over m. This is our contradiction, and this means that our assumption 1 is false. So that means there must exist a z0 such that the polynomial is equal to 0. This is saying that the polynomial has a root, which is what we wanted to prove. Thank you. Please subscribe.